Hello and welcome to today's video. Today's video is for Advanced Geometry, Chapter 10, Section 4, Perimeter and Areas of Similar Figures. So when you were in 7th grade math, you did some area and perimeter stuff where you learned about scale factors and how to use scale factors to take a look at areas. So we're going to do something kind of similar, and I want to derive it. So what we want to do is we want to take a look at scale factor. We want to look at how that affects the perimeter and how that affects the area. So first, I just have a definition of scale factor. Scale factor is a one-dimensional comparison of two objects. So scale factor. A one-dimensional comparison of two, we should call them similar objects. So it could be side lengths, that would be one-dimensional. It could also be circumference if you're looking at circles, anything that's one-dimensional. Okay, so what I have is I have a rectangle, and I'm going to call the first one scale factor 1, and we can quickly find the perimeter of this rectangle. It's going to be 2 of the 3's and 2 of the 4's. So it's going to be 6 plus 8 is 14. And the area, just multiply them together. So that's just going to be 3 times 4 equals 12. Okay. Now what I'm going to do is I'm going to increase the scale factor by 2, which means the one-dimensional units are going to change by a factor of 2. So this would be now 6, and this would be 8. And that's going to change the perimeter because now we have 2 of the 6's and 2 of the 8's. And we end up getting 28 is our perimeter. And if you notice, that's just a difference of 2. So we increased our scale factor by 2, the perimeter changed by 2. But when we look at the area, it's 6 times 8, which is 48. And the perimeter didn't change, or the area didn't change by a factor of 2. The perimeter actually changed by a factor of 4. Okay. I want to do one more. So most of you have done this before, but for this one, this is going to be 9, and h is going to be 12. So this one is going to be now 18 plus 24, and that's going to be 32. Oh, sorry, 42. And if I take 9 times 12, that's going to be 108. And if you take a look at these, the difference between our first one and this one, if you take a look at our perimeter, it increased by a factor of 3. So it's just times 3, so it's exactly what the scale factor is. But if you take a look at the area, it's not times 3, it's actually times 9. So we can come up with a relationship between all of these. If we have any rectangle that has a scale factor of n, well, the length and the width, if it's this 3 by 4, is going to be 3 times the n, and the height is going to be 4 times the n. When we put those together, the perimeter is going to be whatever the original perimeter was times the scale factor. So the original one was 6 by 8, and this new one is going to be just n times that 6 by 8. But the area is going to be the old area, which was the 3 by 4, but not times n, it's actually times n squared. And if you take a look at the formula, you can see where that comes from. So what we end up getting is we get the 3 times the n, and we get the 4 times the n. And the 3 and the 4 multiply, and that was my original area. But then we also get the n's multiplied together, and that gives me the n squared. And when we do volume, you're going to see that we have something similar that happens with volume, except for it's not the scale factor squared, it's actually going to be the scale factor cubed. Okay. So the important things to know from this is that scale factor is a one-dimensional comparison. Anything that is one-dimensional, side lengths, perimeter, things like that, are all going to be the same scale factor. But anything that deals with area is going to be that scale factor squared, and that's how we can compare them. Okay? So what we have is we have a nice little actually, I'm going to get rid of this. So if the similarity ratio of two similar figures is A to B, then the ratio of their perimeters is also A to B, but the ratio of their areas is A squared to B squared. Or you can think of this A over B squared. So if we have figures that we can figure out the area for, or the volume for, then we can obviously use our formulas and figure it out. On a test or a quiz where you're going to have problems is when I give you a figure where you don't have enough information to find the area, and I actually want you to use the fact that you know something about the scale factors and the ratio of their areas to be able to use that information to come up with answers. So for this one, the area of the smaller regular pentagon is about 27.5. What's the best approximation for the area of the regular pentagon? So this is one that we have formulas. We could actually work our way backwards, find the side length, and then use that to find the other figure and do that. But the easiest thing to do is to, we have the area of the small one, okay, and then we also have a comparison of the side lengths. Okay, we cannot just throw those in a ratio and use them because the side lengths are a one-dimensional comparison, the areas are two-dimensional. But what we can do is we can say, well, the side lengths are 4 over 10. So that would be the scale factor because they're one-dimensional comparison. If I want to get to the area, what I have to do is I have to square both of these. And this would be a comparison of the area of the two objects. Now what I can do is I can set up my proportion and I can say, well, it tells me the smaller one is 27.5. So I can put 27.5 here and I can put x here. So that's going to be 16x equals 27.5 times 100, so that'll move it twice. And then divide by 16. So 2750 divided by 16 is about 171.875 actually, exactly. So if you look at my answers, I'm looking for the 172 one. So there's my answers, centimeters squared. So during the summer, a group of high school students used a plot of city land and harvested 13 bushels of vegetables that they gave to a food pantry. Their project was so successful that the next summer the city let them use a larger similar plot of land. In the new plot, each dimension is 2.5 times the corresponding dimension of the original. How many bushels do they expect to harvest? So if we take our original and we increase each of the dimensions by 2.5, then what's going to happen is the new area is 2.5 squared times as much as the original. So if we do 2.5 squared, it's going to be 6.25 times. So we're going to get 6.25 times the amount that we originally did. And at first we got 13. So 13 times 16, whoops, 13 times 6.25. And that gives me about 81.25. So how about we'll round that down, 81 bushels. And the last one, the area of two similar triangles are 50 centimeters squared and 98 centimeters squared. What's the similarity ratio and what's the ratio of their perimeters? Okay, so we have the ratio of their areas. So I'm going to put the 50 over the 98. Now this would be a squared over b squared. So if I want to work my way backwards and find the similarity ratio, I got to square both of these. So a over b is going to be the square root of 50 over 98. We don't want to leave it like that. We want to simplify wherever possible. So the first thing I notice is they both divide by 2. So I can actually make this 25 over 49, which makes this really nice because now I can actually do the square root of the numerator and denominator, so that's 5 over 7. So what's the similarity ratio? The similarity ratio would be 5 to 7 if we did smaller to larger. And the ratio of their perimeters would also be the same as their similarity ratio. So this is both the similarity ratio and the ratio of the perimeters. And that's it for today. Thank you for watching. Have a great day.